Hello everyone, and welcome to AISC's Night School 17, Design of Curved Members / Facade Attachments, presented by Bo Dowswell, Alex Zimmer, and James Parker. Today is June 18th, 2018, and this is Session 1, General Information on Curved Members, presented this evening by Bo Dowswell of ARC International. My name is Brent Liu. I am with AISC's Continuing Education Group, and I will be moderating today's presentation. I want to introduce tonight's speaker, Bo Dowswell, PE, PhD. In 1985, Bo started in the steel industry as a detailer. Since then, he has been involved in both commercial and industrial projects as a design engineer and consultant. He is the principal of ARC International, an engineering firm specializing in research and consulting for steel structures. As a professional engineer, his design practice focuses on steel connections and heavy industrial projects. Bo received a PhD in structural engineering from the University of Alabama at Birmingham, where he's currently an adjunct professor for steel-related teaching and research. Dr. Dowswell regularly publishes technical articles on steel design, and he is a member of AISC's Committee on Specifications, the Committee on Manuals, and also the Committee on Research. He is the author of the forthcoming Design Guide 33, Curved Member Design. With that, I want to welcome our speaker, Bo Dowswell. Bo, thanks for being here, and I'll hand things over to you.
Okay, thanks, Brent. So let's do a quick introduction to session number 1, what we're going to talk about tonight. The first thing we're going to talk about is what is a curved member. And what the design guide does is it breaks down curved members into vertically curved and horizontally curved members. And you can see here this is obviously going to be a vertically curved member because the curvature is in the vertical plane. On the left-hand figure, it's the same structure as on the right hand, but the right hand gives you the finished product. The left-hand figure gives you the project under construction. So another vertically curved member will be this parabolically shaped arch structure for this pedestrian bridge. And it's really, one thing you'll notice is that you can see up here at these two locations for each of these arches, the arch is not exactly vertical. It's going to be kind of tilted over, and some in the horizontal plane, some in the vertical plane. So really, we're not especially talking so much about the that it's a vertical a curvature in the vertical plane so much as we are talking about the behavior. And once we get into the design of these members, I think you'll see what I'm talking about, because the behavior of a vertically curved member is going to be significantly different from a horizontally curved member. One thing about this is that I used this slide in the presentation I did at NASCC, and it just so happens that the Bender Roller was in the audience that supplied the picture to me, and they gave me further information on this. As it turns out, this is in Tempe, and it's made of 16-inch diameter Schedule 40 pipes, and the radius on that parabolic curve varies from 175 to 250 feet. So that's what's called a variable radius curve that we'll talk more about in this session. Okay, that's vertically curved members, but what about horizontally curved? And you can see a simple horizontally curved beam going around the perimeter of this building, holding up at least part of that roof load, and it gives kind of a nice aesthetic effect. That may be the only curved member in this structure, but it kind of creates a nice effect there. And another thing that we're going to use horizontally curved, I mentioned the AASHTO code a second ago, but this is going to be for, say, a light rail transit bridge. So it's not really going to be per the AASHTO specifications, but this is going to be an example of a horizontally curved member. Now this is my favorite one, and the reason is partially because it looks like a UFO, and partially because it shows a lot of things that we're going to be talking about. For example, this goes the whole 360 degrees with only 3 supports here. And so you have a really wide span angle on this horizontally curved member. And you'll notice that if you look closely, and I'm not sure if they did this for the aesthetic effect or for the torsional stiffness, but that's an HSS member. So that tells you one thing, because the HSS members, once we get to session number 3, we'll talk about the torsional strength and stiffness required of these members. And if you look even closer, you'll see that those are end plate connections to the supporting post there. So let's kind of keep that in the back of our mind for session 3 once we talk about the horizontally curved members and connections. Okay, so what we're going to talk about in this session is the first thing we're going to do is kind of give you a general overview of Design Guide 33, and that'll just be a quick run through the table of contents, basically, with maybe a minute or two of description of each of the chapters. And then we're going to go over how to curve steel members. For example, curve geometries. And I know kind of you're thinking, well, how complicated can a curve be? Well, once we get there, we'll talk about the different geometries and the different things that need to be tied up so that these members can be properly bent. And then we'll talk about the bending processes, which, by the way, I'll go ahead and talk about that the bending of these members is typically done by what is called a bender roller company. And there are several available. So you should have one close to wherever you're getting your steel fabricated. And typically these bender roller companies, they specialize only in curving these steel members. And they'll normally be a subcontractor to the steel fabricator, because the steel fabricator, that's a specialized item where, you know, he's not necessarily, the steel fabricator will not necessarily have the proper equipment to do the type of bending that we're going to discuss in this presentation. Okay, next up, we're going to talk about what can you do as an architect, an engineer, a detailer, or a fabricator to get the product that you want in the design stage. So in other words, you're going to send this member that you want to be curved off to a bender roller, but before it gets to the bender roller, even before it gets out of your hands, out of the design office, you need to do certain things to make sure that you get the product that you want. For example, you know, we'll talk about contract documents and things like that, but in this presentation, we're going to talk about curving mechanics, which is going to be required before we can talk about the second and the third items, which is fracture and distortion during the bending operations. All right, so let's get rolling here. This brief overview of Design Guide 33 that's going to be available soon. One thing about the design guide, obviously it's called a design guide, so it's going to have your design guidance in there. And since we've broken these into vertically and horizontally curved members, we've got a separate chapter for each of those. So that's going to be where most of your design equations are. And then it's going to give you some nice information on connections and even some examples on the vertically and horizontally curved members and the connections. But one thing about this is that when I started writing this design guide, I wanted to also, not only did I want to provide all of the equations in a nice design type format in one location. But I also wanted to provide a lot of good practical information. And the reason is because I can remember when I first got into the steel industry, designing structures, the base plate design guide, Design Guide 1 from AISC, back then it was in the first edition. And of course it had all of the equations you needed right there in nice easy format and references for you if you wanted to go do more advanced calculations. But also it had all the practical information there for you. For example, if you had a certain size anchor rod, what size plate washer do you need over your oversized hole in your base plate? And things like that that you really can't find in other locations, and they were all contained right there in one small document, Design Guide 1. Another one is things like grout holes. For what base plate size do you provide grout holes? So I wanted to kind of carry that over. So what I did is I tried to provide as much good practical information as I could, and I talked to a lot of the bender roller companies to try and get their input on this. And you can kind of see the finished product once the design guide comes out. But it's got information in there also on detailing, which is kind of a little different from what you would get in a normal design guide. But I felt like it was really important to provide specialized detailing information for these curved members. The contents of Design Guide 33, Chapter 1, is going to talk about essentially the things that we discussed when we looked at the photographs. What are the typical applications for the vertically and horizontally curved members? So this is going to be primarily to use in the conceptual stages of a project. Also, it contains a little bit of information about industrial type structures in there that we won't really talk about too much today, but the design guide has information on industrial structures. So when is a spiral type curve used in an industrial structure, for example? So Chapter 1, you're not going to spend too much time in there if you're an engineer looking for design equations. Chapter 2, we're going to talk about today. It's going to be on curving steel members, and it talks about bending geometries and processes used by the bender roller. Chapter 3 is designed for bending. We'll also talk about that today, and it discusses the prevention of fracture and distortion during the bending operation. So once you design your member, you have a final design, say, you also need to go back and make sure that it can be bent properly, because the member during the bending operation, as we'll see today, is subjected to more stringent requirements in the bending operation than it should be during the service life of the structure. So that's what Chapter 3 is all about, design for the bending operation, to make sure you get the product that you're expecting. Chapter 4, fabrication and detailing. It talks some about tolerances. Otherwise, as an engineer, you may not spend too much time there, but as a fabricator and detailer, you may that may be your main chapter. Chapter 5 is general design issues, and this is kind of a location where I put a lot of things that you're probably not going to use unless you have a special situation. The one exception is that I've got information on contract documents in there, which I think everybody should probably review, and we'll talk about that some today and probably at the very beginning of session 2. One perfect example of that you probably will not go to Chapter 5 for material properties unless you have special case. And I'll tell you why. Because material properties of bent members are typically going to be about what you would get from a fabricated straight beam or a straight column. You know, the fabrication process is going to change the material properties for both straight and curved members. But as with straight members, if you have a structure that's exposed to very low temperatures, you could potentially have problems with brittle fracture. So, and the same thing goes for straight members, but I've just got information in Chapter 5 for you on curved members. Okay, so that's the type of thing you go to Chapter 5 for, under special conditions, with the exception, like I said, of contract documents. Okay, Chapter 6 and 7 is going to be vertically and horizontally curved members. That's where the bulk of your time will be spent if you're an engineer. If you're a structural engineer, that's where all of the equations are. Chapter 8 is design examples, and we'll cover 2 of the 3 design examples in session 4. We have 2 vertically curved design examples and 1 horizontally curved design example in Chapter 8. And the glossary, now the glossary I thought was very important too, because once I started going into the Bender Roller Committee meetings, and they were kind of, you know, my background is in civil engineering. And I've been in structural engineering since I got out of school in detailing. And some of the things that they were discussing in there, I just didn't understand the terminology they were using. So the link between civil engineering and the Bender Roller companies, some things can get lost in translation there. So the glossary is pretty important to be able to link where we can all communicate together. And I'll show you some really good examples of that in today's session. So that's one of the minor goals of the secondary goals of today's session, is to kind of introduce you to some new terminology potentially. And last but not least is the list of Bender Roller companies at the very end, and you'll see why we put that where it's easily accessible at the very end of the booklet later on in this presentation. Now let's move on to curving steel members. And the first thing we're going to talk about is curve geometries. And this may sound pretty simple. And the very first one, standard bends, is pretty simple. But once we get into the specialty bends, there's a lot of information that you'll need. And we're going to go over each of these specialty bends that I have listed here. So what is a standard bend? A standard bend is just what you would think a standard bend is. You can take a look at these 3 figures. That's a standard bend. The first thing that is required to call a bend a standard bend is that it has to be a single radius curvature. All right, the second thing is, for a standard bend, it has to be bent about a principal axis or a geometric axis. All right, and here's some of the terminology that I said we would introduce. Hard-way bending is what the Bender rollers call bending about the strong axis. If I'm a structural engineer, I generally think of bending about the strong axis rather than hard-way bending. But the Bender rollers typically call that the hard-way bending. And easy way bending, of course, is going to be member bent about the easy way, which is bending about the weak axis. Okay, so here's an example, and there's a table in the design guide with a lot of different shapes in there. We're not going to go over all of these, but we'll cover several. For example, the first one is probably the most common, the I shape, and you can see bent hard way and easy way on the left and right hand sides of the slide respectively. Now one thing I wanted to notice too on these slides is the radius. The radius I have tied up in this figure is the radius that the detail dimensions should give that radius to the inside of the flange for a wide flange and to the centroid of the member for easy way bending. Now, of course, as engineers, we're probably going to build our finite element model using the centroid of the member, and then the detailer would come back on his detail drawings and, of course, subtract off half depth to get the radius shown here. That doesn't happen all the time. Sometimes the bender roller just has to go in there and make the calculation himself. For HSS, we've got round, which the radius is going to go to the center of the round HSS, or for square and rectangular, the radius will go to the inside edge of the curve, so the compression side of the curve. And of course, here's the hard way and easy way bending of the HSS. Channels, the weak axis are for the two figures on the left, and strong axis, or the hard way bending, is for the figure on the right. Okay, and the figure on the right, of course, you can see the radius goes to the inside of the inside flange, and for what is called flanges in and flanges out by the bender rollers, goes to the back of the channel in both cases. For T-sections, you have stem in and stem out. It's kind of difficult to tell whether it's strong axis or weak axis bending with a WT because the section properties can vary depending on the axis. So you've got stem in, stem out, and both of those dimensions, radius dimensions, go to the flange, and stem up where the radius goes to the centroid of the member. And this one is kind of interesting, the angle. This will be the last one we talk about. It's got the radius goes to the leg, to the outside or the inside of the leg, and this is leg in and leg out. And those two figures on the left are for geometric axis bending, and then you have principal axis bending about the minor axis on the right-hand two figures, where the radius goes to the hill, the corner of the two legs. Okay, so that was kind of a really long explanation to what a standard bend is. So now we'll move on to all of those various specialty bends that we saw in that list earlier. The first one we'll discuss of these specialty bends is the off-axis bend, and that's when you bend about a non-principal or non-geometric axis. Bender rollers call this conical rolling sometimes, and here's what it looks like. You can see how this could be called conical rolling, because if you can imagine a cone-shaped plate structure, this edge of the flange, of the wide flange, would fit right on that cone structure. These are used a good bit for roofs and canopies, like I've got shown in this figure. Here's the curved member. If you look down in plan view, that's going to be a radius curve, but then the member is tilted over in this off-axis angle to be at the same angle as the roof slope. All right, next up is compound bends, and that's where you have two or more arcs in the same plane. So it's basically two simple curves, and it can either be one member that is bent twice, or it can be spliced right here at the tangent point with two standard bends that are spliced together. All right, so one thing about the compound bend is that there's no reversal of curvature. Another thing is that your tangent points do not have to line up. You can have a straight segment between the tangent points, like I've got shown here. So you can have this straight segment in there, and that may even be easier for them to curve as one single member if they do it that way. All right, so now you take the compound bend and reverse the radius, put a radius on the other side, and we call that a reverse compound bend. This is also known as an S-curve, and it can also have a straight segment between the tangent points. And this is going to be a reverse compound bend. I believe the figure on the left shows a monorail beam. That's probably the only thing we discuss, as far as I can remember, about industrial structures. That might be the only figure I've got in here for that. On the right-hand side, that could potentially be a roof structure. That might even be the one that I've got coming up on the next slide. So these reverse compound and the compound bends are typically used for the same thing as the off-axis: canopies, roofs, architectural features, and you can see the nice effect that it has on the roof here and on the canopies on the right-hand side there. All right, next up is multi-axis bends, and these are where you have curvature about more than one axis. It's otherwise known as multi-plane bending, and here's the type of curve that you're going to get. So essentially, with the figure on the right, I'm not exactly, that it looks like a lifting beam or something to me, but the figure on the right, you can kind of see, you can almost get any shape that you want. We've got these names for all the shapes, but you can come up with your own shape, a three-dimensional shape, and send most of these bender rollers a CAD file, and they can fabricate whatever you want. Okay, probably one of the most popular ones, and I showed you the parabolic curve up there earlier in the presentation, is going to be the variable radius bend. And that's going to be any non-circular bend, also known as multi-radius bends. So probably the most popular is the parabolic, and the reason for that we'll talk about in session 2 is because parabolic arches are extremely efficient for resisting uniform gravity loads. And if you want to kind of get into the history of all this, you can kind of go and see the the old arches that were made out of materials that had no tension capacity. So you're basically just putting up blocks with the keystone up there, and it holds itself up, plus whatever's above it, whatever load it's carrying, just in compression. So we'll get into that once we start talking about vertically curved members. All right, we have a pedestrian bridge on the left where the parabolic curvature of that cord is carrying the load from the pedestrian bridge deck. And the figure on the right, I'm not sure if that's just kind of an aesthetic thing or if it's actually carrying weight, but this is from one of the bender rollers that sent this to me, and I believe this has to be on the Chicago riverfront. I don't know if anybody has actually seen this structure or not, but I'd like to take a trip up there and see it when it's complete. Okay, so the parabolic is one variable radius bend. Another one, actually, you can have any shape you want with this, but the other standard shape is going to be the elliptical shape. And these can be required where you have a curved plane that interfaces, that intersects a skewed plane. And two examples here, the left-hand figure has a curvature in the vertical plane, and then you have the member bent. It has to be bent to an elliptical shape because it's tilted out at an angle away from the vertical there. And a similar thing happens on the right-hand figure, where if you look down in the plan view of this roof structure, you have a radius, but because this truss is tilted upward at an angle, you end up having to make that into a elliptical curve. Okay, and the last one we're going to talk about are the spiral bends. And I think everybody knows what a spiral bend is. A spiral stair is typically what these are used for. And I'll let you kind of, if you're interested, look up the strict definitions of spiral and helical curves. But one's a two-dimensional curve and one's a three-dimensional. But we kind of use those interchangeably now in the construction industry because everybody knows that figure that I've got up there is a spiral stair stringer, right? And this is also called sloped rolling or pitched rolling. And the reason is because you need extra wide rolls to roll these things. And I'll show you what I'm talking about later when we get into the bending methods that are used. So there's a typical spiral stair on the left-hand figure, but on the right-hand figure, that's kind of a really, I'm not even sure if that's actually a true spiral or not, but it's a really dramatic art sculpture that was formed by steel by one of the bender roller companies. All right, so now that we know what these curves look like, let's take a look at the bending processes that are used by the bender rollers. And there are reasons why we're going into this, and it has to do with some things like tolerances and distortion and things like that. So let's get through this information on the bending processes, and then we'll talk about the reasons that we need that information later in this session and at the start of session 2. All right, there are two basic ways of bending steel, cold bending and hot bending. Now, hot bending is going to be when you heat the member up, and essentially that lowers the strength of the member, lowers the yield strength of the member so that it's easier to bend. Cold bending is not something where you bring the temperature down in a refrigerator or something like that. It simply means that you bring the member in, and whatever room temperature is, whatever the temperature in the shop is at that time, they bend it. So obviously the cold bending is typically going to be a little more economical because you don't have that extra step of heating the member up. Now the 3 bending processes that we're going to talk about in this presentation are the top 3, the pyramid roll bending, incremental step bending, and induction bending. There are many more processes that are used. These are the 3 that are common to structural steel fabrication. You can look in the design guide to get further information on the other processes, but a lot of the other processes are used for things like the piping industry, or to make small bends, small diameter bends on very small members that would be used for things like furniture or fixtures or things like that. So pyramid roll bending, let's start off with this one. This is probably, or actually it's not probably, it is the most popular method to bend members. And it's called pyramid roll bending because it has 3 rolls, these 2, and then one on the other side that are in a pyramid shape. Now this can be in the vertical plane or the horizontal plane. If you have a small member such as an angle or a small channel, typically the machine is going to be a smaller machine that's in the vertical plane. But most of the things that we'll talk about in here, for example, Y flanges and HSS members, will usually be, the 3 rolls will be in the horizontal plane. So this is a, let's go back to this, and I'll show you a little more about what happens. The member, this member is the rolls are adjusted. The 3 rolls are adjusted, and the member is put into the machine, and it's fed through. You know, as it goes through, it'll be fed through, and then, you know, when I was a steel detailer, I kind of just imagined that it bent the member, and they took it, put it on a truck, and they were done. But they feed it through one time, all right, and then they adjust the rolls, and then they feed it through again, and then they adjust the rolls again. So they move the rolls closer to each other to get slightly more curvature with every pass through the machine, and then eventually you end up with the curvature that you're looking for. One other thing I will say about this is that you often have these supplementary rolls, and we'll talk more about those later on. There's your supplementary rolls. The 3, this one, and this one, the 3 red ones are your main rolls, and you can see that it's bending this W24 at 117 member, so that's a pretty big member to be bending, and especially with, say, a cold bending type process. And then these supplementary rolls, there's one here, and then there's one that you can't see on the opposite side of the web. All right, so it looks something like this. If you look through, this is the member that's being bent, this is the main roll, and these 2 are the supplementary rolls. So the supplementary rolls put a tension force on the tension flange. Here's your compression flange, and here's your tension flange. So it puts a tension force on the tension flange to control any web distortion that is caused by this very large compression load that's exerted by the machine onto the curved member. We'll talk a little more about that later. Pyramid roll bending, can you also use contoured rolls like is shown here for the round HSS member that is being bent. And of course, I think we all know that those provide support during the bending operation. And the different bender rollers will have different rolls. They may have rolls already in whatever size pipe you would need. If you have an odd shape built up type round member built up of plate, they probably will not have that roll available, so there will be some tooling cost involved if you want to do a pyramid roll bending of that member. So if you're building 300 of these curved members, that's probably not an issue, but if you're building one, it would probably be pretty expensive to have it rolled with these contoured rolls. On the other hand, the contoured rolls may not be required because it may be a large radius and you may not have much distortion without the contoured rolls. This slide I wanted to put in there has the contoured rolls for this extruded shape. I just kind of wanted to put that in there to quickly show you that essentially you can dream up any shape you're interested in, and you can have contoured rolls for that shape made. It's just a matter of paying the tooling cost, and is it going to pay off if you only have 10 of these members versus 1,000? And this is what I call special rolls. And what happens if you look at these flanges? This is going to be your tension flange. This is going to be a wide flange bent the easy way. So half of this flange will be in tension, that's this half, and half will be in compression, which is this half. Same thing on bottom. You got compression here, tension here. So the tension flange, just like a service load, if a service load were applied, the tension flange that would be would not be the tension half of the flange would not buckle in a local mode, but the compression portion of this flange may buckle in a local mode. So to prevent that local buckling or the out-of-plane movement or distortion, you can have these grooved rolls where the flange fits within the groove, and the groove braces the flange against out-of-plane buckling, or otherwise known as to bender rollers as cross-sectional distortion. And this figure, it just shows a similar thing for a WT. You can, if you look closely, you can see that's a WT over here at the end, and you can see that the flange fits nicely in that groove to prevent any movement. And then you have compression in the stem. That looks like a really high depth to thickness ratio on that stem, so it's probably going to be subjected to when it's subjected to compression stresses, it's going to potentially buckle due to that compression stress. Otherwise, you can brace it like shown here, where it kind of fits nicely into that groove, and it prevents buckling in the out-of-plane direction. All right, moving on from the pyramid bending to the incremental step bending, and this will be the only slide on this, and one reason is because this is proprietary. That's the best figure I could get for this, and it's really difficult for me to even tell what's going on here, but what is happening in this figure, you see a lot of these bending methods are proprietary, so it's kind of difficult for them to share the information because they want to use the machinery that they've spent a lot of money trying to develop, so they want to use that to their advantage. So they don't want too much of the information to get out, and rightfully so. So the member, this looks like an HSS, a rectangular HSS, so it's fed through, and if I remember correctly, it's fed through in this direction. Okay, and there's a machine behind all of this here, but this part of the machine grabs the HSS member here at this location, and then it pulls back, and I believe it pulls back in the direction opposite of that green arrow I just put there. So it pulls back, and back behind the figure, it's the member is clamped, so you get a cantilever bending type action when the machine pulls in that direction. All right, so you pull that member, get the cantilever bending action, and then it releases, and then you feed it through again, and you do the same thing. You feed it through again, so you incrementally feed this thing through and pull on it until you get the correct shape of member that you're interested in. All right, so incremental step bending, and it's the same as pyramid roll bending. Both of those are cold bending methods. But next up, we're going to talk about the only hot bending method that is commonly used in structural fabrication. And what happens is you can see there's an HSS member here and an induction coil here, and as that HSS runs through at a constant rate through this induction coil, and the induction coil heats up this narrow strip of the HSS right all around the perimeter of the HSS member. And after that heating, the member is bent by force. And I'll try to describe what's going on here. This is a much bigger induction bending machine than the one I showed you on the last slide. You can see the person here operating it, and you have these really big round, it looks like built up out of plate, round sections built up out of plate with a really high diameter to thickness ratio. And one thing you'll notice from this figure, or from that part of the finished product there, is that from here I can't see any distortion in that. Which is something that's very important to notice for a member that has this high of a diameter to wall thickness ratio. So what happens in the induction bending process? The member this is the red hot part that's been heated up by the coil. That red ring goes all the way around the perimeter, and everything from there back, all of this part right in this area, all of this part of the member back here is straight, and it's being fed through the induction bending machine in this direction at a constant rate. Then it hits this part where it's heated up by the induction coil, and then immediately after that you can see the water cooling here, and as it's being fed through, it pivots about this radius arm, which is this part of the machine. So the radius arm grabs the member as it's coming out of the machine, and it pivots about, there's a pivot point right over here. You can't see it because it's blocked, but it pivots about a point over there and creates a radius in that circular member. You can see the water cooling. So you've only got a narrow strip there, which the cooled parts on both sides of that narrow strip, this side and this side, tend to naturally brace that member against distorting. So you can get really high depth to thickness ratios with minimal distortion using this method. One thing to notice is that equal thickness elements are obviously going to give you uniform heating around the perimeter. That's not to say that things with unequal thickness elements can't be induction bent. It's just to say that it might be a little more difficult. Induction bending is usually going to cost more than cold bending, but it's capable of small radius bends with low cross-sectional distortion. And here's one thing that's probably not on too many people's radar, and it probably shouldn't be at this point if you're designing things that go inside buildings. But going back to the thing that we talked briefly about earlier, about if you have an exposed structure that's exposed to very low operating temperatures, low service temperatures, this may be helpful, or something that's for some reason is subjected to brittle fracture in some way. With proper control, and I'll emphasize this part, with proper control of the essential variables, meaning the heat input and the cooling rates and things like that, the material properties can be enhanced over the virgin material properties of the member, of the straight member. And the reason for that is because this is essentially it provides kind of a stress relief to the member. So it's kind of a heat treatment, or really it is heat treating the member. It's just a matter of if you control the variables properly to get the heat treatment that you're interested in. Now this surprised me. I talked with many of the bender roller companies, and they verified that you can bend almost any shape that you're interested in with this. Up to 6 inches thick have been successfully bent with induction bending. Okay, so to conclude this part about bending processes, each of the bending methods has advantages and disadvantages. The capabilities of each bender roller vary significantly, and that goes for the personnel, their equipment. Some may have wide rolls that can bend spiral stairs, and some may do the induction bending, and some may specialize in the bending of heavy shapes, about the strong axis. So and usually they will refer you to the guy down the street type of thing if they don't specialize in what you're looking for. So they can tell you who to go to. It's pretty important, especially if you have something that's a little out of the ordinary, or if you have a very tight radius that you want bent, a member bent to a tight radius. You want to involve the bender roller early in the design process, hopefully in the conceptual stages. Okay, let's move on to design for bending. Now, what we're going to talk about is what do you need to think about as an architect or an engineer or a detailer or designer when you're designing these members, when you're designing a structure that's going to be curved, have curved steel in it. And one of the things that I wanted to talk about, this is one of the major questions that we get on curved members in the Solution Center. And the question usually comes in something like, I have a W14 at 90, and I need to know what the minimum radius that can be bent to. And the answer is that there's not an actual answer. The answer is usually to contact the bender roller to find out. I thought this was interesting. You can see this is from kind of an old copy that I've had since 1985. When I first got into the steel business as a detailer, I was given a copy of this. It came from either U.S. Steel Design Manual or one of the Bethlehem Design Manuals. And you can see it's old enough. It goes beyond 85. It goes way past that because they're designated in the WF. That's the way they used to call out a wide flange shape instead of just using the W. So this is a pretty old rule of thumb, but they had this information in there, and you may not be able to read this small writing, but what this says is that the radius can be anywhere between 10 and 14 times D. That's your minimum radius that you can bend this member about the strong axis to, where D is the total depth of the member. Okay, but remember, this is from, way before 1985, so it's old technology that was used to develop this rule of thumb. And I thought it was interesting because I actually took this into the bender roller committee meeting, and they said I needed to throw this away because new technology, they just need to give us a call and find out what the minimum radius is for each specific case. Okay, so if rigid guidelines are not available, what is the minimum radius dependent on? First of all, the bending axis. Is it going to be bent the hard way or the easy way? Shape of the cross-section, slenderness of the cross-section, bending method and equipment that the bender roller uses. And these two are for the designers and architects, the level of acceptable cross-sectional distortion and also the level of acceptable cold working of the material. So they're going to ask you those two questions if you call a bender roller. How much distortion is acceptable? We'll talk more about that at the very first of next session. Here's the list of bender roller companies. Like I said, we're going to have the list at the end of the design guide, but for now, if you need that list, go to the AISC website, and that's the link to the same list that will be in the back of Design Guide 33. All right, let's talk about curving mechanics. And we're going to use curving mechanics. I mean, not that I want to talk about a lot of theoretical things, but curving mechanics will be used to talk about fracture and cross-sectional distortion. So if you go back to, say, a sophomore level mechanics of solids class, you probably will remember seeing something like this, where if a beam is bent into the elastic range, the stress distribution looks like that, and if it's bent into the plastic range, it looks something like that. And then the inelastic stress distribution is somewhere in between that. Also, what you know from that sophomore level mechanics class is that if you stress something on the elastic part of a stress strain curve, which is this linear part, then you just get a spring back and you have no permanent curvature. So what that means is that for anything that you need a permanent curvature in, you're going to have to be either on the plateau. That's where your low curvature bends are going to be, or your large radius bends, and your small radius bends or your high curvature bends will be somewhere up here in the strained hardening range. That's about as high as you're going to go, probably, about that arrow. But if I mean, you're not going to get up to these points. You're not going to strain it that much during the bending operation. It will be one of the first two arrows. Continuing with the mechanics class that we all learned as sophomores, the maximum strain in a member is simply Y sub O divided by R, where Y sub O is the distance from the neutral axis of the member to the outermost fiber. There's Y. Y sub O goes from here to here, and R is the centroidal radius. Now, in strengths of materials, we talked about the elastic bending strength of members and stresses due to bending of the member. But in this case, R is going to be the radius of curvature. Okay? So let's take this equation and assume that our member is symmetric, so that Y sub O is equal to half the member depth. I'm calling D the member depth. So D divided by 2R is going to give our maximum strain in the element. All right, so if this starts sounding like it's getting a little too theoretical, the reason that we're doing this is because we have this alpha. We can also define the maximum strain using this alpha. And what alpha is the strain ratio. So the maximum strain is going to be alpha times the yield strain, which is the yield stress divided by the modulus of elasticity. Okay, so if you set that equation on the previous slide equal to this equation, we know, if we know the radius and we know the member size, we know the yield strength, which we should all have that information even in the preliminary stages of design, we can solve for alpha. Okay? So for each member that's curved to a certain radius, we know what alpha is. And the reason we went through all this trouble is because this research done in 2006, published in the AISC Engineering Journal, your hub day found that for alpha greater than 12, that's kind of getting into the realm where you want to start contacting the bender roller. For alpha less than or equal to 12, you can probably go about your design and not worry about whether the bender roller is going to have problems or not. So, so anything above alpha equals 12, you probably want to stop right there and start contacting a bender roller to find out what is going to be necessary to make your member work during the bending process. It's not that anything above 12 is going to give you problems. It just means that it may cost a little more. They may have to make a mandrel to go inside your HSS member or something like that to keep distortions down. Okay, just briefly, we'll go through alpha and kind of what it means. These first two are just put up there for fun. In normal design, if your beam, and this is not for curved members, it's just if you load a beam up and load it to 97% of the plastic moment, you'll end up, and I'm just trying to give you an indication of what the magnitudes of alpha are. You'll have somewhere between 2 and 3.5 for alpha. All right, so all that inelastic action causes an alpha up to 3.5. So your conservative limit here is 12. Strain hardening for 50 KSI material starts at 8.7, which is way beyond where you get for just normal bending up here. And I put two more values here, 3% and 5%. If you talk to a bender roller, a lot of times they'll say this is generally the upper limit on what can be done, but that's way above the 12, the 29 there. So you know, special things need to be done above 29, and 3% is also kind of a reasonable upper bound for your members. So the 3% is pretty safe in almost all cases. So if you go above the 12, then you're probably still safe up to 17, but somewhere in that range is where you want to start contacting people and finding out if you have a problem. All right, fracture during the bending operation. Let's talk about the what can potentially happen. Now, most of the time you're not going to be too worried about this because, first of all, fractures typically is not going to happen during the bending operation, especially if you have a low alpha. High alpha increases the risk of fracture or low ductility. Now, typically it's going to be the job of the bender roller to tell you, or you know, discussions with them should reveal if you can bend a member without fracture. But in this section, I'm just going to kind of give you a brief look at what kind of essentially not to do. And this is a perfect case. I would not cut a diamond-shaped hole, and this may seem obvious, in a member before you bend it. If you want a diamond-shaped hole in your member, I would probably wait until after you bend the member and then cut the diamond-shaped hole. It's going to be less economical to do it that way, but to prevent fracture, that's probably the route you want to go. If you have a small circular hole, it may be a different story, but that's kind of a judgment call at that point. So how is ductility decreased? Holes, cuts, copes, and welded fittings. If you weld something on before bending, that can cause trouble too. Okay, so that's just in general, but let's talk about tension flange bolt holes. Okay, and I'm talking about holes that are going to be on the tension edge during the bending process. So they're going to be on the outer edge of the member. And this is really only for wide flange shapes, but in general, you can kind of generally apply it to all shapes. For holes formed before bending, your beam line will only accept straight members. So to feed that member through the beam line is economical for a fabricator. So he would rather fabricate, the fabricator would like to form the holes before the bending operation is complete. That's only acceptable for large radius bends. For small radius bends, you would be wise to fabricate those holes after the bending operation, but it's more expensive because you can't use the beam lines. There are really two limit states to worry about fracture and excessive hole elongation. This rule of thumb is going to be published in the design guide when it comes out, and it's primarily controlled by hole elongation. Now, if you follow this equation, you can form your holes in the tension flange of a wide flange shape before bending. All right, even for small radius bends. Now this is kind of a difficult inequality to satisfy. It's very similar to the equation in specification chapter F, where you have F sub U, the ultimate stress, times A sub Fn, which is the net area of the tension flange, has to be greater than or equal to 1.1 times the yield stress times the gross area of the flange. All right, so if you satisfy that, even for small radius bends, you can be satisfied that you should not get hole elongation in your member if you form the holes before bending. All right, let's talk about distortion during the bending operation. And we'll talk about what to do with what we're going to learn today at the very beginning of next session. But distortion is any deviation from the cross-sectional shape of the original member. It occurs in every member to some degree because any initial imperfections from the mill get amplified during the bending process. It can be in a single half wave, a series of wrinkles along the entire bending length, and it's also called waving or wrinkling. That terminology is primarily used by the bender rollers. All right, this figure, if you look really close, shows kind of a local buckling distortion in the web of an HSS member that was curved. So you can get, due to that flexural compression, you can get flange or web local buckling in the member. Also, you have a high shear stress between, especially for the pyramid roll bending, between the rolls, so you can get a shear buckling contribution. You can get contact force distortion. Typically, it's going to be something similar to web buckling or web crippling in this area due to that high compression force from the roll. And like we said before, you can control that with these supplementary rolls. For really tight radii, you can't completely make it go away, but you can control it. One thing, if you get too high of a force applied to these supplementary rolls, you can get flange bending. So let's take a look at what happens to this flange potentially. And this is an extremely rare case, but I want to show you all the different types of distortion. You can see the bending that occurred right here and right here in this member where those flanges are bent locally because the supplementary rolls pressed on those parts of the flange and bent that flange out. So you can get things like that. You can get things from the radial forces during the bending operation caused by, because there's a compression force in the flange, but the flange is curved. All right, so this force in the flange has a vertical component to it, which has to be resisted by that web. We'll talk more about this next time because this occurs for service load design too. But you get a couple of different things. You get web buckling due to that compression force in the web. And before the flange force gets into the web, you can have flange bending like this. So we'll talk a good bit more about that for service load design next time, but just be aware that this type of distortion can occur during the bending operation. So, after all of that, the distortion can be affected by many different things, including, obviously, a tighter bending radius will give you a higher alpha, so that's going to affect your distortion. the cross-sectional shape of the member and the cross-sectional dimensions of the member, primarily the slenderness of the element, the bending axis, weak or strong bending or off axis, the bending method and techniques used by the bender roller, and the level of initial geometric imperfections in the member. So if you look at the ASTM tolerances straight out of the mill, you'll have some level of geometric imperfections. And those, like I said before, will be amplified during the bending operation. Okay, so these can be reduced. I will say this, over the next 3 slides, we replaced the word affected by, with reduced by. So you might want to take a look if you downloaded the notes and change that wording there. And the reason is because it's more specific. Cross-sectional distortion is reduced by cross-sectional support. If you have these special rows like we mentioned earlier, you can see that the flanges are guided by those grooves, and that's a very tight radius on that wide flange member. Supplementary rolls, we've already shown you this before, so we won't spend any time on that. Cross-sectional distortion is also reduced by mandrels, or something else that can be either put inside or outside of a member. In this case, we've got an HSS stair stringer that's being curved to a spiral shape, and to support it during the bending operation, they put 3 smaller HSSs in there, and it looks like they tack welded those in, and it did a really good job of supporting that member in this case. A couple of slides from now, I'll show you the case done by the same fabricator where it didn't quite work out. Sometimes you just have to do trial and error. I'll show you that in just a second, but it looks very similar to the figure up here. Now for wide flange shapes and angles and other open shapes, we really don't have a good measure of distortion. But for square and rectangular HSS, we do have a good measure of distortion, and it's measured by the distorted shape that I've got shown on the screen up there. You end up with a concave compression flange and outward bowing of the web. And we've even got nice equations to plug in that are dependent on B1, which is the distortion out from wall to wall, divided by B, which is the original cross-sectional dimension of the shape before it was bent. And then we have rho sub F, which is for the flange, the compression flange to be exact, and it's measured by E, which is this inward bowing dimension, divided by D, which is the depth of the member. So what we're going to do when we talk about tolerances is we're going to measure those and talk about those in terms of rho sub W and rho sub F. And as promised, I'm going to show you this distortion picture where you can see the inward bowing. This is the same thing we had up there before, the same bend that had the 3 HSSs in it, but this one only had 2. It looks like those are distorted a little bit themselves. And you can see a little bit of bowing in this side wall too. So that's a real case where they just had to throw the member away and start over with try it again. One thing I will mention on this is a little deceiving because this report was done in 1988 with pyramid roll bending and no internal support by a mandrel. Nevertheless, you can see the distorted shape. If you have a thin-walled member, it looks something like that, just like what I had up there on the drawing a couple of slides ago. And if you have a thick-walled member, there's very little distortion. For round HSS, there's also this measure of distortion rho, and this is going to be your primary mode of distortion, this ovalization for round, and you have this minimum and maximum dimensions of the ovalized shape, and you have d sub n, which is the nominal outside diameter of the original shape. So you just calculate some percentage of rho based on those pre-bent and post-bent dimensions. We'll talk more about this next time. Now, one thing to know, we have a lot of things going on with these special roles and supports on the internal and things like that of these members, but just in general, just in concept, the distortion, the resistance to distortion is approximately is similar to the local buckling resistance. So lower B over T ratios lead to less distortion. Using that same concept, round elements will perform better than rectangular elements during the bending operation. Stiffened elements will perform better than unstiffened elements. And one final thing to note, and I'll say this again, I believe in the next presentation in session 2, is that the bending operation often requires a lower slenderness than required for strength under service loads. So once you get your member designed, you may, for service loads, you may still have some work to do. Okay, we're down to the final 2 slides, and we're going to stick with the local buckling analogy here. And what I did is I went in and took a look at some of the data that was supplied by the bender roller companies to me on certain size shapes, and I found out that I wanted to provide some practical rules of thumb to you. So if you look in AISC spec section B4.1, if your member is compact, lambda is less than lambda p for all of the elements within a cross section, that's going to get you at least a medium radius bend. All right, so generally that's going to be sufficient for a minimum alpha of 4, but I would be very comfortable going all the way up to 9 if lambda is less than or equal to lambda sub p. All right, but if you're going to use restrained elements or mandrel or special rolls or something like that, your alpha can be much higher. So if you're in the design process, the early stages of design, and you end up calculating alpha equals 4, there's no reason to even stop and waste your time calling a bender roller at that point, unless you just want to get his schedule on when he can get something done. Okay, we'll take it one step further, and if you're like me, I'm on the East Coast, so I don't do a lot of seismic design, but if you look in the AISC seismic provision section D1.1b, there's a thing called lambda sub HD, which means highly ductile, and it's more stringent than lambda sub P. So I decided to take advantage of those too and take a look at the data that I was just talking about on the last slide. So if lambda is less than or equal to lambda sub HD, that's good for a small radius bend. And one thing to note on this is that even with those stringent requirements, the bender roller may say, well, I think I can bend this member, but it would be better if you bumped the element thickness up by 1/8 and went to maybe a slightly larger size W14 than what you've got. So that's the type of thing that you can discuss with the bender roller. All right, so that concludes the session 1 presentation. And Brent, I'm going to turn it back over to you.
Okay, thank you, Bo. And as the slide says, we are opening things for questions. If you have a question, feel free to send that through the chat feature anytime right now. We do have a few questions, Bo, but before we get to those, we got a couple questions for our audience. We have 2 polling questions, and let's see if the concepts you presented tonight are sticking with our audience. So here's our first polling question. Which of the following is a hot bending process? A, pyramid roll bending. B, incremental step bending. C, induction bending. Or D, rotary draw bending. You can click on the radio button of the answer you believe is correct, and we can get a good feel of the results that are coming in, and we'll talk about it. Again, which of these four is a hot bending process? Pyramid roll bending, incremental step bending, induction bending, or rotary draw bending? All right, I'm going to go ahead and close the poll. And Bo, it looks like overwhelmingly people got this one as C, induction bending. What do you think?
Yes, that is correct. And hopefully the visual way back here in the early part of the, or maybe the middle of the presentation will help with that. Actually, there's two good representations. The induction bending, remember, has the induction coil that heats up the member before the bending operation.
All right. Good job, everybody. Let's do one more question, polling question, and we'll move on to your questions. The next question. Which cross-sectional element type is most susceptible to distortion during the bending operation? Is it A, round elements, B, rectangular stiffened elements, or C, rectangular unstiffened elements? Again, which of these three cross-sectional element types is most susceptible to distortion? And rapid responses are coming in for answer C, Bo. Do you agree?
Yes, that's correct. And remember, because we were going back and discussing the local buckling of these elements, that distortion is kind of analogous to local buckling, where we said that round elements are better than rectangular elements based on that analogy, and then the stiffened will perform better than the unstiffened elements based on that same analogy.
All right, very good. With the time we have left, let's answer some questions that came in. The first question is in regards to cambering a beam versus curving. Most fabricators that I work with can camber beams pretty much with any camber I request. At which point does camber become exceeded by curving and then fall outside of the ability to be produced by a typical fabrication shop?
Okay, that's, yeah, your typical fabrication shop has a setup to do cambering, which is going to essentially provide a small radius, or I'm sorry, a small curvature or a large radius curve about the strong axis of a beam. So cambering and is a curvature that is intended to offset the gravity loads on a beam. All right, so what is typically done in a cambering machine is a two-point ram bending. And if you take a look in the design guide, it discusses that briefly, but I know that that there's some work being done on a camber design guide too, so it'll have more information on that when that comes out. So the typical fabrication shop can provide the camber. So they would hire a bender roller once it comes to either, if they had to camber something that exceeds their machine capacity, either they could heat that member up or they could send it to a bender roller. And the bender rollers sometimes get big contracts to to camber the members too. So there's kind of, the question is not really, necessarily cut and dry, because, like I say, the bender rollers can be contracted to camber all the beams on the project. So when does I think your question is more of, when do the fabricators have to go out to get their members curved? What can they do in-house versus what do they hire the bender rollers to do? And I'm not sure exactly what the radius there. I don't think there's a radius in there, but I think if you're putting camber to offset the gravity load in a beam, most fabricators are going to have the equipment to do that for normal size beams, say up to, I don't know, I'll just throw out a number. It's going to be different for every fabricator, but something like maybe a W24 or W27 they could probably handle, some of the bigger fabricators. If you get bigger than that, or if you have a really tight radius, you're going to have to go to a bender roller. And I really don't have a specific cutoff for you, but the fabricator and your bender roller can tell you more about that.
Okay. Next question. How do you prevent the relaxation of the curve during shipping and erection?
Okay, there's some information in the design guide on this, and that's a good question. And the question is, first of all, does that really happen? And the second question is, if it does happen, what to do about it? And being that we really do not even have an answer for the first question, then we really can't answer the second question. But there's been some, there's a study out there that discusses the loss of camber, for example, due to the vibrations on a truck, and it's been said that the same thing happens to curved members that are curved to a tighter radius than a typical camber. There were some in the bender roller committee. This was discussed for kind of a heated discussion in the bender roller committee, and some of the bender roller committee members felt like it did happen, that the relaxation due to the shipping vibration did occur, and some said, well, it's probably just due to the handling of the member. Maybe it gets knocked around while it's being put on or taken off of the truck that causes it. And there were some that said that induction bending was performed better for this relaxation, but really we had no proof of that. One reason that could be true potentially is that the residual stresses in induction bent members are less than in the other members. So it is kind of a topic that I really don't know the answer to, but I do know that they provide bracing. If it is kind of a long, slender member that's going to vibrate on the truck, they will provide bracing for the shipping of that member to prevent any distortion or loss of radius during the shipping.
Okay, I think we have time for one last question here, and we'll wrap things up. The next question is, how will galvanizing affect a shape after bending?
Okay, and that's another topic that's discussed in the design guide, and this is something that I kind of did. It's kind of similar to the last question, in that there's not really a real answer, because it's dependent on the residual stresses that are in the member. So you have certain residual stresses, and the cold bending methods are going to be a little higher than the are a good bit higher than the induction bending residual stresses. And then once you put in, dip it into the galvanizing, it's going to release those residual stresses and change the shape of the member. So the question is, this is another thing that I've discussed with the bender rollers. Sometimes you can do it and everything works out perfectly. You don't have to worry about anything. You can cold bend it and dip it, and it works out fine. Sometimes you cold bend it, dip it, and the radius changes. So you have to go back to the bender roller at that point and run it back through. If they did pyramid roll bending, run it back through the machine, which kind of tends to damage the galvanizing when you do that. So do you want to send it back to the galvanizer, or what do you do about that? So it's really a question that, once again, I really don't have a good answer for you. I'm just trying to give you all of the information that I have on it. And it is something that I've looked into and asked all of the experts in the field on I think all three of these questions. And we really do not have a straight answer for you, other than that, you just have to, if you want a galvanized member, you kind of have to just try it and see where it goes. And in most cases, galvanizing has been successful. And there's the issue of cracking during galvanizing too, which it's been successful without warping or loss of radius or cracking in most cases. But you do run the risk of every now and then you're going to end up possibly delaying the schedule by having to send it back to the bender roller.
Okay. All right. Thank you very much, Bo. We are more than out of time here. Thanks, everyone, and have a good night.